Welcome back. So this week we are covering a new topic, thermodynamics. This is Dr. Reber again. I guess I should mention Mr. Skrbashevsky is fine. I'm doing this topic. Apparently Mr. Skrbashevsky had a bad experience in his qualifying exams with thermodynamics, so he has kicked the topic over to me. So in any case, over the course of Physics 201 and 202, we've generally focused on mechanical motion, so the motion of objects. So this has included looking at the energies of objects moving through gravitational, electric, magnetic fields. So in mechanics, objects are governed by Newton's laws, and they deal with kinetic energy and various other kinds of potential energy that an object may obtain. So this week we're going to study thermodynamics. Thermodynamics deals with the internal energy of systems, and it's governed by a different set of laws called the laws of thermodynamics. One of the challenges of dealing with thermodynamics is that we're no longer looking at the motion of a single object. Instead, we're looking at something like 10 to the 20th power atoms or molecules in a system. Because of this, we will be thinking about the properties of groups of atoms. So rather than thinking about something like a force or acceleration, we'll be thinking about things like temperature, heat, density, or composition of a system. Also, we're going to focus on equilibrium systems, so systems in which these properties, the temperature, the density, the pressure, the composition, they are all uniform throughout the system, and they remain constant without some kind of external action causing them to change. The central concept of thermodynamics is temperature. So this word is familiar, and you've probably built up, we all have a sense of hot and cold, that we can sort of measure the temperature just by touching a thing with our hand. So we have to be a little careful because sometimes our intuition is incorrect. A surprising example of this is when you touch a cold piece of metal and a cold piece of wood. If they are both exactly at the same temperature when you touch them, the metal will actually feel colder than the wood. The reason is that the metal conducts heat better, so it feels colder despite being the same temperature. So to get started with thermodynamics, we need to understand temperature. The properties of many substances change with their temperature. Say the length of a metal rod increases when you increase their temperature, the volume of a liquid expands when you raise the temperature, and pressure of a combined gas increases when the temperature goes up, for example. So we can use one of these properties to measure a temperature. We can watch the volume of a sample of mercury change and then use that to compare temperatures. We haven't defined temperatures quantitatively yet. This is just to tell if two things have the same temperature or if the temperature of something is changing. If we take two objects, one hot and one cold, we can use our device to see that the hot object has a higher temperature than the cold object. If we wait and the two things are in contact with each other, the hot object will transfer heat to the cold object, and eventually they will come into thermal equilibrium. That means that the hot object will get cooler and the cold object will get hotter until they are both exactly the same temperature according to our device. And at that point, the temperature will no longer change. If we add a third object that only touches one of these objects, then when it reaches thermal equilibrium, then all three objects will have the same temperature, even the two objects that are not touching each other. Okay, this seems pretty obvious. You can tell that it was sort of obvious to scientists because they called this the zeroth law of thermodynamics because they developed, well, the first two at least, and they didn't realize that they needed a zeroth law until 20 or 30 years later because, this is something that is a necessary point to make. But this point is important. If you put the two things together, when they reach thermal equilibrium, when their temperature stops changing, they have the same temperature. This suggests that there is something universal about temperature, that when a block of wood and a block of metal are in contact with each other and they reach the same temperature, then something about their internal energy is identical. Okay, so we want to use temperature in a more quantitative way. So the logical way of doing this is picking a physical process that reproducibly occurs at a certain temperature and then set that as our reference. So we have three common scales for measuring temperature. We have degrees Celsius, we have Kelvin, and we have degrees Fahrenheit. We can choose the process that we compare with to be the freezing point of water, and then set that to be our standard temperature in Celsius to be 0, and for Fahrenheit we set that to be 32 degrees. The next standard we want to use is the boiling point of water, so we set that to be 100 degrees Celsius and 212 degrees Fahrenheit. That means if we want to convert from Fahrenheit to Celsius, then we use the conversion factor shown here. First we subtract 32 degrees from Fahrenheit and then multiply it by 5/9. That then gives us the temperature in Celsius. The reverse conversion from Celsius to Fahrenheit is to multiply the temperature in Celsius by 9/5 and then add the 32 to get the temperature in Fahrenheit. So these are pretty basic conversion factors and they shouldn't give you too much trouble. Kelvin is the other temperature scale, and this is the absolute temperature scale. And to convert to Kelvin, basically you add 273.15 to the temperature in Celsius to get the temperature in Kelvin. Notice that in Kelvin, the 0 is set for absolute 0, the lowest possible temperature. So we'll discuss that a bit more in the future. But Celsius and Kelvin are the standard SI units for temperature, but because most of you think it's Fahrenheit probably, it's worth being able to do the conversion. So for an example here, we're asked what is the temperature 100 degrees Fahrenheit in Celsius. So we use our conversion factor. 100 degrees Fahrenheit minus 32 gives us 68. We multiply that by 5/9, and that gives us a temperature of 37.8 degrees Celsius. So now you know a temperature of about 38 degrees Celsius outside is really hot. So when the temperature of something rises, the object tends to expand. One example of this is a meat thermometer. So inside of the thermometer there's a twisted piece of metal that expands when it heats and it contracts when it cools down. As the metal expands, it uncoils and it is connected to a dial, so as the metal uncoils, the dial turns. When it cools back down, it returns to its original setting. So to a pretty good approximation, this expansion is linear and proportional to a coefficient of linear expansion called alpha. So to find out how large the expansion is, you multiply this alpha, this coefficient of expansion, by the length of the object times the change in the temperature. That then gives you the change in the length of the object. I have an example here. Let's say you are laying railroad tracks and you are putting them down at 0 degrees Celsius. This is a place where the temperature can hit 40 degrees Celsius. So how much of a gap do you need to put between the lengths of the rail? The rails are 12 meters, and the coefficient of linear expansion here is 2 times 10 to the minus 5 inverse Celsius. So to calculate this, we use the change in length is equal to alpha, the linear coefficient, times the length times the change in temperature. So we multiply 2 times 10 to the minus 5 inverse Celsius, the coefficient we are given, by the length, 12 meters, by the change in temperature, which is 40 degrees Celsius. So we do this and we get 0.0096 meters, or 9.6 millimeters. Notice this is a decent-sized gap, almost a centimeter. So if you don't do this, then on a hot day, these tracks will stretch and warp horribly. Notice if you laid the tracks on a warmer day, say 20 degrees Celsius, then the gap you would need to leave is half the size. The point here is that you have to be a little careful about thermal expansion. If you're working with something that fits perfectly now, it is possible that at a different temperature it will not fit very well at all. So this sets us to think about the classic thermometer, a bulb filled with mercury or alcohol, and this mercury or alcohol then expands or contracts depending on the temperature of the bulb. Notice this is a liquid. So that means the volume of the liquid expands, and the liquid will then flow to conform to the shape of the container. The way to think about this is that the volume of the liquid expands. So it will try to expand linearly in the x, y, and z direction. That means that the volume will increase, but the coefficient of the volumetric expansion is 3 times that of the linear expansion. Because most of the mercury or the alcohol is in the bulb in a thermometer, a small change in temperature leads to a small change in volume, but because the column of the fluid has a small radius, it leads to a pretty large change in height. So this volumetric expansion can be used to measure the temperature pretty accurately. Okay, so you guys have some questions to answer. I think this set should be pretty straightforward, so good luck.